In the infinite darkness of space, a lone traveler, a relic of human ambition, has defied all odds. For 45 years, it has journeyed through the cosmos, venturing farther than any human-made object ever has. Launched in 1977, this ancient probe was never meant to survive this long, yet it continues to send whispers from the edge of the unknown. But on October 22nd, 2017, its instruments screamed with an urgency that shook the scientific world to its core. A discovery so shocking, so impossible, it left astronomers speechless and sparked a mystery that has haunted experts for years. This wasn't just another data point, it was the most powerful gamma-ray burst ever recorded, a cosmic spectacle that shattered every expectation and challenged everything we thought we knew about the universe. Today, we unravel the enigma of this mind-blowing event, diving deep into why this outburst was so extraordinary and how it has left researchers grappling with questions that could rewrite the laws of physics. Buckle up, because what this probe uncovered is nothing short of staggering, and the truth will leave you awestruck. Picture this: two twin probes, identical in every way, launched into the vast expanse of space in the late summer of 1977. Their mission was simple, yet audacious: to explore the outer planets of our solar system, snapping pictures of Jupiter, Saturn, Uranus, and Neptune, and sending back data about their moons and rings. Back then, scientists gave these probes just 5 years to complete their task. 5 years. Yet here we are, nearly half a century later, and these cosmic pioneers are still out there, defying time, distance, and the harsh realities of space. They've traveled over 24 billion kilometers, a distance so vast it takes light more than 22 hours to reach us from their position. These probes weren't built for this. They were never designed to venture into the uncharted waters of interstellar space, the mysterious realm beyond the influence of our sun. But that's exactly where they are now, and what they've found there is nothing short of revolutionary. Let's rewind to 2012, when the first of these probes crossed a boundary no human-made object had ever breached: the heliopause, the edge of the sun's protective bubble, known as the heliosphere. This is where the solar wind, a stream of charged particles from the sun, gives way to the interstellar medium, the sparse matter and radiation that fills the space between stars. Crossing this threshold was like stepping into a new dimension, a place where the rules of our solar system no longer apply. The second probe followed 6 years later, in 2018, and together they've given us a front-row seat to a part of the universe we could only dream of exploring. But interstellar space isn't just a vast, empty void. It's a wild, dynamic frontier, teeming with secrets that challenge our understanding of the cosmos. And on that fateful day in 2017, one of these probes stumbled upon a secret so profound it sent shockwaves through the scientific community. The signal came without warning. Racing through interstellar space at 60,000 kilometers per hour, the probe's instruments suddenly lit up, detecting an unprecedented surge of high-energy radiation. This wasn't just a blip on the radar, it was a cosmic alarm bell, signaling something catastrophic had occurred in the depths of space. 19 hours later, the effects of this event reached Earth, overwhelming nearly every observatory in our arsenal. Telescopes designed to detect gamma rays, the most energetic form of light, were blinded by the intensity. The data was unmistakable. This was a gamma-ray burst, but not just any burst. It was the brightest, most powerful gamma-ray burst ever recorded, a phenomenon so extreme it earned the title of the boat, the brightest of all time. With an energy of 18 tera-electron volts, it shone 70 times brighter than any gamma-ray burst ever observed. To put that in perspective, this single event released more energy in a few seconds than our Sun will emit in its entire 10 billion year lifetime. It was a cosmic explosion of unimaginable scale, and it left astronomers reeling. Gamma-ray bursts are the universe's most violent events, born from the deaths of massive stars or the collisions of neutron stars. They're like cosmic fireworks, releasing torrents of energy that can outshine entire galaxies for a brief moment. But this burst, catalogued as GRB22109A, was different. It didn't just break records, it broke the rules. When astronomers analyzed the data, they found anomalies that didn't fit our models of how these bursts behave. The afterglow, the fading light that follows the initial explosion, was unlike anything we'd seen before. It contained a strange new component in the radio spectrum, something that defied explanation. The jet of radiation produced by the burst was also bizarrely focused, narrower than any jet ever observed, and it exhibited behaviors in other wavelengths that left experts scratching their heads. For months, the scientific community was abuzz with questions. What could have caused this? Was it a fluke? Or had we stumbled upon something entirely new? At first, theories ran wild. Some speculated that the burst was triggered by the collapse of a massive star into a black hole, a process that can produce powerful gamma-ray bursts. Others wondered if it was the result of two neutron stars colliding, a cataclysmic event that sends ripples through space-time and unleashes torrents of energy. There was even talk of more exotic possibilities. Could this be evidence of dark matter interacting with the probe, or, in the wildest of fringe theories, a signal from an advanced extraterrestrial civilization? The truth, when it finally emerged, was both surprising and humbling. In April 2024, the James Webb Space Telescope, the most advanced observatory ever built, turned its infrared gaze toward the source of the burst. What it found was astonishing. The culprit was a supernova, the explosive death of a massive star. But this was no ordinary supernova. It was a stellar monster, 20 times the mass of our Sun, and its explosion was unlike anything we'd seen before. So why was this supernova so bright, so powerful? Astronomers are still piecing together the puzzle, but the leading theory is that it was a special kind of explosion, driven by the rapid rotation of the dying star. When massive stars collapse, their cores can spin so fast that they produce tightly focused jets of particles, shooting out into space at nearly the speed of light. If these jets are narrow and concentrated, they can create an incredibly bright and energetic beam of gamma rays. In the case of GRBB22109A, the jet was one of the narrowest ever observed, which could explain its record-breaking intensity. But even this explanation raises more questions than answers. Why was the jet so narrow? Were there other factors at play, like unusual magnetic fields or interactions with the surrounding interstellar medium? The truth is, we don't know yet. This discovery has exposed gaps in our understanding of stellar explosions, and it could take years, maybe decades, to fully unravel the mystery. But the story doesn't end with the gamma-ray burst. This impossible discovery is just one chapter in the epic saga of these twin probes. Since crossing into interstellar space, they've been rewriting the textbooks on what we thought we knew about the universe. Take the heliopause, for example. Before these probes, scientists assumed the heliosphere, the sun's protective bubble, was shaped like a comet, with a long trailing tail. But data from the probes revealed something astonishing. The heliosphere is round, almost perfectly symmetrical, like a cosmic beach ball. This finding turned decades of assumptions upside down and forced researchers to rethink the structure of our solar system's boundary. Then there's the plasma, the charged particles that fill interstellar space. When the first probe crossed the heliopause, it detected a sharp drop in plasma currents, followed by violent turbulence as it entered the interstellar medium. Scientists thought this meant the heliopause was a thick, unstable boundary. But when the second probe crossed 6 years later, it told a different story. It passed through the heliopause in just half a day, detecting no plasma lull or extreme turbulence. Instead, the boundary appeared thin and stable. How could two identical probes exploring the same region of space have such different experiences? The answer lies in the sun's activity cycle. The first probe crossed during a solar minimum, when the sun's magnetic field was weaker, allowing interstellar magnetic fields and cosmic rays to penetrate deeper into the heliosphere. The second probe crossed during a solar maximum, when the sun's magnetic field was stronger, stabilizing the heliopause. These differences highlight the dynamic, ever-changing nature of our solar system's edge, a place where the sun's influence battles the forces of the interstellar medium. The probes also confirmed the existence of a cosmic barrier, a magnetic wall just inside the heliopause that acts as a shield against cosmic radiation. This barrier, created by magnetic currents flowing toward the heliopause, is stronger and more dynamic than anything within the heliosphere. Every 11 years, when the sun's magnetic field flips, this barrier reforms with opposite polarity, a process that could have profound implications for how we protect future spacecraft, or even human explorers, from the harsh radiation of interstellar space. These discoveries are a testament to the probe's enduring legacy, but they also underscore how little we still know about the universe beyond our solar system. The heliopause and interstellar space are part of a complex, interconnected system, and we've only scratched the surface of its mysteries. Yet, as incredible as these findings are, they come at a cost. These probes, now in their 5th decade, are showing their age. Technical glitches and sudden losses of contact have become all too common. Their power supplies, generated by decaying plutonium, are dwindling, and engineers have been forced to implement a strict power-saving plan, shutting down non-essential instruments to keep the probes alive. Of the original 10 instruments on each probe, only 3 remain active. Every byte of data they send back is precious, a fleeting glimpse into a realm we may not revisit for generations. NASA hopes to keep the probes operational into the 2030s, but time is running out. When their power finally fails, they'll drift silently through the cosmos, carrying golden records etched with the sounds and images of Earth. A message to any intelligent life that might find them. But until that day comes, they continue to beam back data that challenges our understanding of the universe and reminds us of the audacity of human exploration. The gamma-ray burst of 2017 wasn't just a scientific milestone, it was an emotional one. Imagine the astronomers who received that first signal, their hearts racing as they realized they were witnessing something historic. Picture the engineers who've spent decades nursing these aging probes, coaxing them to keep going despite impossible odds. Think of the dreamers who, in 1977, dared to send two small spacecraft into the unknown, never imagining they'd still be teaching us nearly 50 years later. This discovery is a reminder of humanity's relentless curiosity, our unyielding desire to push beyond the horizon and uncover the secrets of the cosmos. It's a story of triumph, of resilience, and of the profound connection we share with the universe. But the implications of this discovery go far beyond a single gamma-ray burst. It raises questions that strike at the heart of our understanding of the universe. Why do some supernovae produce such extreme bursts while others don't? Could these events have played a role in the early universe, shaping the formation of galaxies or seeding the cosmos with heavy elements? And what about the anomalies in the burst's afterglow? Could they hint at new physics or even phenomena we haven't yet imagined? The James Webb Space Telescope, with its unparalleled ability to peer into the distant past, is already helping us search for answers. In 2025, it discovered another record-breaking supernova, one of the earliest and most massive ever seen, dating back to just 2 billion years after the Big Bang. This finding suggests that stellar explosions in the early universe may have been fundamentally different, with higher energies and unique properties that we're only beginning to understand. The probe's discoveries also have practical implications. Understanding the heliopause and the interstellar medium could help us design better spacecraft, capable of withstanding the radiation and magnetic fields of deep space. It could inform our search for life beyond Earth, as we learn more about the environments where planets form and evolve. And it could even protect us here on Earth. Gamma-ray bursts, though rare, have the potential to disrupt our atmosphere and technology if one occurs close enough. By studying events like GRB2 2109A, we can better predict and prepare for these cosmic threats. As we speak, the scientific community is racing to analyze the data from this impossible discovery. Teams around the world are combing through observations from the James Webb Space Telescope, the Fermi Gamma Ray Space Telescope, and other observatories, searching for clues to explain the burst's unprecedented brightness and bizarre behavior. Some are exploring whether magnetic fields in the interstellar medium could have amplified the burst's energy. Others are investigating whether the supernova's progenitor star had unusual properties, like an exceptionally high rotation rate or a unique chemical composition. And a few are daring to ask whether this event could be a sign of something entirely new, a phenomenon we don't yet have the tools or theories to comprehend. The emotional weight of this discovery is impossible to ignore. It's not just about numbers or data points. It's about our place in the universe. These probes, launched by a generation long gone, are our eyes and ears in a realm we may never physically reach. They carry our hopes, our dreams, and our insatiable need to know what lies beyond. Every signal they send back is a gift, a reminder that we are part of something vast and magnificent. And when they finally fall silent, they'll leave behind a legacy that will inspire generations to come. The gamma-ray burst of 2017 was a wake-up call, a cosmic shout that there's still so much we don't understand. It's a challenge to keep exploring, to keep questioning, to keep reaching for the stars. In the years since that historic event, the probes have continued to surprise us. In 2023, one of them detected unexpected spikes in magnetic field strength and plasma density, suggesting it had entered an unknown region of interstellar space. This finding reported in 2025, has sparked new debates about the structure of the interstellar medium and whether our probes are approaching a boundary we didn't know existed. Some speculate it could be a region of dense, charged particles created by the interaction of solar and galactic winds. Others wonder if it's a pocket of dark matter, the mysterious substance that makes up a quarter of the universe's mass. Whatever it is, it's another reminder that interstellar space is far from the empty void we once imagined. It's a vibrant, complex place, full of surprises that challenge our assumptions and ignite our imagination. The James Webb Space Telescope has also added to the excitement, revealing new details about the universe's most dramatic events. In 2024, it captured the first detailed images of a supernova remnant, Cassiopeia A, showing intricate layers of gas and dust sculpted by the explosion of a massive star. This remnant, just 340 years old, is a window into the processes that create the elements we're made of: carbon, calcium, iron. Every atom in our bodies was forged in the hearts of stars, and discoveries like these remind us of our deep connection to the cosmos. Webb's observations of ancient supernovae, some dating back to when the universe was just 1 billion years old, are helping us understand how these explosions shaped the early universe, seeding it with the building blocks of galaxies, stars, and planets. But perhaps the most profound impact of this discovery is the way it makes us feel. It's humbling to think that a small probe, launched decades ago with technology that's now obsolete, could uncover something so monumental. It's thrilling to imagine what other secrets are waiting out there, beyond the reach of our telescopes and spacecraft. And it's inspiring to know that even as these probes near the end of their journey, they're still teaching us, still pushing the boundaries of what we believe is possible. This impossible discovery is a testament to the power of human ingenuity, the courage to explore the unknown, and the endless wonder of the universe. As we look to the future, the legacy of these probes will live on. New missions are already being planned to follow in their footsteps, equipped with advanced instruments to probe the mysteries of interstellar space. The Nancy Grace Roman Space Telescope, set to launch in 2027, will survey the galactic plane, searching for more light echoes and supernovae to study. The European Space Agency's Euclid telescope, launched in 2023, is mapping the universe's expansion, helping us understand the forces that drive cosmic evolution. And here on Earth, scientists are developing new theories and models to explain the anomalies of GRB 22109A, hoping to unlock the secrets of stellar explosions and the physics that governs them. But for now, let's pause and marvel at what we've achieved. 2 small spacecraft, launched in an era when smartphones didn't exist and computers filled entire rooms, have traveled farther than anyone could have imagined. They've survived radiation, micrometeoroids, and the relentless passage of time, sending back data that has transformed our understanding of the universe. The gamma-ray burst they detected in 2017 was more than just a scientific breakthrough. It was a moment that captured the awe and wonder of exploration. It reminded us that the universe is full of surprises, that there are still frontiers to cross, and that our journey into the cosmos is far from over. So what does this discovery mean for you, sitting there watching this story unfold? It means you're part of something bigger. It means your curiosity, your desire to learn, connects you to the scientists, engineers, and dreamers who made this moment possible. It means the universe is speaking to us, and we're listening. The signal from that probe, sent from 15 billion miles away, is a message from the stars, a reminder that we're not alone in this vast cosmic sea. It's a call to keep exploring, to keep asking questions, to keep chasing the impossible. And who knows? The next discovery could be even more shocking, even more profound. The universe is waiting. Let's go find it. This is the story of a discovery that changed everything. A discovery that proved the universe is stranger, wilder, and more beautiful than we ever imagined. A discovery that showed us the power of human ambition and the resilience of two tiny probes that refused to give up. The gamma-ray burst of 2017 wasn't just the brightest of all time, it was a beacon, lighting the way to a future where the impossible becomes possible. So let's honor that legacy. Let's keep looking up, keep reaching out, and keep exploring the infinite wonders of the cosmos. The stars are calling, and we've only just begun to answer. Thank you for joining us on this journey through the wonders of space. Your support makes it possible to continue sharing the marvels of the universe with the world. We can keep exploring the stars and uncovering the secrets of the cosmos. Until next time, keep looking up